All right, today's our introduction to logarithms. Logarithms are not new to you. You saw them in Algebra 2, but they're new to this particular class. First set of skills we're going to be addressing, can we focus on if you have something that's in a logarithmic form, can you rewrite it into an exponential form? Or if you have something in exponential form, can you rewrite it into a logarithmic form? Okay, so using the exponential as your point of reference, if you have a to the y power equals x, that's the same thing as y is equal to log base a of x. Now we do have some restrictions. The x has to be greater than 0. A has to be greater than 0. And a can equal 1. As far as why those restrictions are in place, I'm going to focus on the exponential form right here. Okay, if we let a be a negative number, if you take a negative number and raise it to various different exponents, it bounces back and forth between being positive and negative if you restrict yourself to integers. And then as soon as you start throwing in fractions and decimals in the exponents, then you get places where it's undefined. So it's not a smooth curve by any means if a is allowed to be negative. We're not going to allow it to be 1, because 1 to be anything is just 1. And we're not going to allow it to be 0, because 0 to be anything is just 0. So as far as this to have any meaningful set of rules, as far as to examine as a family of functions here, we need to have these restrictions in place. And then the last one I didn't address, the byproduct of this thing being greater than 0 and not 1 is the fact that it forces this to be greater than 0. All right, on to some practice problems now. We want to write this in exponential form. That's 4, it's the subscript, that's the exponent, equal to 1024. So log base 4 of 1024 equal to 5. That equation, written in exponential form, is 4 to the 5th power equals 1024. This is 36 to the negative 1/2 power equals 1/6. So a quick review of some exponential stuff. 1/2 power is the same as square rooting. Square root of 36 is 6, and that negative puts it into the bottom of the fraction. All right, reversing that, this is log base 4 of 1/16 equal to negative 2. This is log base 49 of 7 equal to 1/2. Okay, another way of thinking about logarithms that works well for some people, it's what power does this have to be raised to in order to produce that number, negative 2? What power does this have to be raised to in order to produce 7? All right, due to the nature of our environment that we've talked about many times, all of our quizzes and tests will be calculator active. Historically, teaching this class, there would always be at least one assessment in Chapter 3 where you were forced to be able to perform certain skills without a calculator. Even though calculators are allowed, you want to have a certain mental math ability here and not be calculator reliant on always plugging numbers into the calculator. So these are some examples of things you should be able to do by mental math and not be relying upon a calculator. So log base 2 of 32, that's equal to some number that we want to know what it is. Now if it happens to be a set of numbers that you don't quite visualize very well, you can make an equation out of it. You've got x, this is 2 to the x power equals 32. In other words, x has to be 5. Okay, 64 to the what power gives you 8. If you can answer it as is, great. If not, you can make an equation out of it. And then once you have an equation like this, you can treat it the same way we did day 1. We spent a day talking about how to solve these types of exponential equations by making both sides powers of the same base. So that's going to be 1/2. To get from 64 to 8 by using exponents is 1/2 power or square rooting. 7 to the what power gives you 1. Anything to the 0 power gives you 1. Okay, 9 to the what power gives you 27. This is a good example to review the skills from earlier this week. That's 9 to the what power gives you 27. Rewrite that as 3 squared to the x equals 3 to the third. 3 to the 2x is equal to 3 to the third. X is equal to 3/2. Okay, log base 8 of 8. What power do you have to raise 8 to in order to get 8? 1. Okay, log base 17 of 17 to the 105. Well, what power do you have to raise 17 to in order to get 17 to the 105? Well, 105. We'll write that one out. Oops. Okay, nice shortcut to know. It's going to be useful when we do equation solving in a couple days. If that matches this, it always reduces to just the exponent. So if that's like log base 8 of 8 to the 50th, it's just 50. Those two are the same, it just reduces to the exponent. Alright, the two most widely used logarithms are log base 10 and log base 8. If you see a log without an exponent, that's understood to be base 10. And that's also known often as a common logarithm. A log button on your calculator, all scientific calculators, all graphing calculators have a log button of some sort. If it's log without a subscript, it's understood to be base 10. And the other commonly used log is base e. This is extremely rare to see log base e. Log base e is known as the natural log, which is universally abbreviated as ln. So going back to a couple of quick examples of going from exponential to logarithmic and logarithmic to exponential. Log of 24 equals x. If you want to write that exponentially, that's understood to be base 10. So that's 10 to the x power is equal to 24. Now it's not asking us to solve for anything, it's just asking us to rewrite it. So this would be 10 to the 15th power equals z. Okay, rewrite each of the following exponential equations in logarithmic form. So this would be log base 10 of z is equal to 7/3, and you very rarely see the base 10 written. You'll see it more written like this. And this would be log base e of 17 is equal to t. You almost never see it written as log base e. It's ln of 17 is equal to t. All right, next item for today, the change of base formula. The change of base formula isn't quite as critical as it used to be because of features that are more widely available on varying different calculators, but we still need to know it for other reasons, and not all calculators do have it. If you have a simpler scientific or a very old graphing calculator, it may not have the feature that I'm going to show you in a moment. All right, so the change of base formula. Log base a of x. A represents the base that we don't want. B represents the base we do want. Typically, we want to convert something to base 10 or base e, because base 10 and base e are the buttons that pretty much any scientific calculator will have. And that's one of the main reasons for doing the conversion. Not the only reason. It does have its place in higher level problems, but for now, that's what we're focusing on. So, log base 5 of 50. Okay, just as a quick mental math strategy here, what this is saying is 5 to the what power gives you 50. Well, we know that 5 to the first is 25. I'm sorry, that's a lie. Say 5 to the second is 25. 5 to the third is 125. The 50 is somewhere between 25 and 125. So we know that the value of this expression is 2 point something. It's got to be somewhere between 2 and 3. So how could we get a more precise value of just more than 2 point something? If we converted that to a base 10, that would be log of 50 divided by log of 5. Or if we converted it to base e, that would be ln of 50 divided by ln of 5. So without using any advanced features on this calculator, just the log or the ln button, we can do log 50, close parentheses, divided by log 5, and you get about 2.43. Or if we did base e, we could do natural log of 50 divided by natural log of 5. Same 2.43 number. Doesn't matter what base we convert it to in terms of you're allowed to convert it to anything. Just that if you were going to use a traditional, not very advanced calculator, you would want to go base 10 or base e. Okay, the newer graphing calculators, if you go to the math button, and then I think it's all the way down the bottom of this, there's a log base function, and you can actually type it into whatever base you want it to be and get the number directly. In terms of like the history of calculators, so to speak, that's a relatively new feature that wasn't widely available on calculators up till current generations. If you have an older graphing calculator, you may not have that. So it makes a lot of the uses of this change of base formula obsolete. But again, as I said, there's still other reasons why you need to know it. Okay, one more quick example over here. Log base 100 of 30. If we wanted to convert that to base 10, that would be log of 30 divided by log of 100. If we wanted to convert it to base e, that would be natural log of 30 divided by the natural log of 100. Or, for the purposes of just getting a numerical value, we can use the log base feature on our calculator. And that's about 4.19. So it actually had 3 decimal places. 4.992. Didn't follow my own instructions here. 2.43. All right, next thing we're going to talk about, solving some simple log equations. And we're just going to do some real basic ones today. And we're going to revisit solving more complex log equations in a couple lessons from now. Okay, for today, the equations that you're responsible for are going to be in one of two forms. It's either going to be log equal to a number or log equal to log. Okay, we don't have to do any pre-writing, so to speak. There's no algebraic manipulation to do before getting to the key steps here. If you have log is equal to number, sometimes it's mental math. Just by visual inspection, you can observe what the answer should be. If not, what you're going to do is rewrite that exponentially. That's 4 to the second power equals 2x minus 8. And then solve the equation that remains. So 4 squared is 16. Bring over that 8. X is equal to 12. Okay, log equations have a high risk of extraneous solutions. This thing here has to be positive and not equal to 1. This thing here has to be positive. Those are our restrictions when we're dealing with logs. Since this is where the variable is at, that's where we're focusing our attention. If we plug this in there, does that stay positive? If it causes it to be negative, it's extraneous. If it doesn't, it's a keeper. Well, 2 times 12 is 24. 24 minus 8 is 16. That's positive. This is a keeper. Now, the fact that that's positive doesn't guarantee that 12 is correct. It just identifies it as not being extraneous. Okay, next example. You have log is equal to number. Rewrite that exponentially. X minus 1, quantity squared is equal to 16. Solve this. Take the square root of both sides. We're introducing an even root to start with. Make sure you do the plus minus. Minus 1 equals plus or minus 4. X equals 1 plus or minus 4. So we have 2 possible solutions to consider. 5 and negative 3. Okay, this has to be positive, not allowed to equal 1. Okay, that's a keeper. That's not. That's extraneous. Now let me emphasize here that we are not throwing away the negative 3 because it's negative here. We're throwing it away because of what happens when we plug it in. This answer itself down here, in general, can be negative as long as it doesn't cause any type of violation in our domain range issues when we plug it back into the original. Okay, second algebraic structure. Log equals log. As long as those bases match, they're both base 17, we can simply set these two guys equal to each other. 3v minus 4 equals 4v plus 2. So I'm going to bring this over here. That makes it 1v. Bring that over there. That makes it minus 6. And now we have to check to see if this is extraneous. That has to be positive. 3 times negative 6 is negative 18. Negative 18 minus 4, it's negative something. This equation has no solution. And again, we're not throwing it away because it's negative here. We're throwing it away based on what happens when we plug it in. Okay, one more example of this type. These are both base E. It's a single natural log on the left, single natural log on the right. Set these guys equal to each other. This one we've got to do a little bit of factoring. Bring that 3x over here. Bring the minus 1 over. And then we have to check to see, are these guys extraneous or are they keepers? So we plug in a 5, 25 minus 9, we're good. 15 plus 1, we're good. Negative 2 quantity squared is 4. 4 minus 9 is negative 5. Once it fails once, it causes any violation in the restrictions, it's extraneous. We don't have to check any further. So we have one that worked and one didn't. All right, last issue we're going to look at for today, inverses. All right, if you have a basic logarithmic function, like these two guys, you can expect the inverse to be an exponential. If you have a basic exponential, like one of these two guys, you can expect the inverse to be a log. When they blend together and they get a little bit messier like this, it's not quite so predictable. I don't know if we'll do all of these. We'll do a couple. Okay, so number 1, we have y is equal to log 2x plus 1 minus 5. If you're finding the inverse of a function, x becomes y becomes x. Domain becomes range becomes domain. And then what you want to do is resolve this equation for y. So to solve that for y, we're going to want to get that 5 over here. That gets log equals, instead of a number, an expression. So we have a similar situation that we did here, except it's slightly more complicated. We're going to rewrite that exponentially. That's 10 to the x plus 5 power is equal to 2y plus 1. Now keep in mind our goal is we want to rewrite this as a y equals equation. Subtract 1. And then divide that whole thing through by 2. So we get y is equal to 10, the x plus 5 minus 1 all over 2. So that and that, those guys are inverse functions of each other. We're not going to go through the graphing part today, but if you were to graph those two guys, they would be mirror images of each other across the y equals x line. And the graphing of logarithms is a topic for another day, just being complete in terms of the idea of dealing with inverses. Okay, algebraically finding an inverse means the x becomes y becomes x, then resolve for y, And then the importance in terms of graphing is these guys are mirror images of each other across the y equals x line. All right, let's do, we did 1, let's do 4, we'll do an exponential. Y is equal to e to the 5x minus 3. We want to find the inverse of this. This is a relatively basic exponential, so we expect its inverse to be a log. X becomes y, y becomes x. Solve this for that y. I'm going to bring over the 3. And then I'm going to rewrite this logarithmically. This is log base e of x plus 3 is equal to 5y. Divide by 5, and then write that in a more appropriate form as ln of x plus 3 over 5. So this guy and this guy, they are inverses of each other. Graphically, if we were to graph them both in the same coordinate plane, they would be mirror images of each other across the y equals x line. All right, let's do one more. Let's do one that's got like a blend. Let's do 3. That's got an exponential inside of a logarithmic. So let's see how this plays out. So y is equal to log base 3, 5 times 2 to the x plus 9 minus 3. Okay, x becomes y becomes x. We want to solve this for y. So that means we want to get that 3 over to the other side, or the minus 3 over. Now that we have the log by itself, we're going to rewrite this exponentially. This is 3 to the x plus 3 power equals 5 times 2 to the y plus 9. Okay, keep in mind, our goal is we want to solve for this y. So now we want to isolate this right there. Subtract 9. Divide by 5. And the last thing we can do to solve that for y is rewrite it logarithmically. So that's log base 2 of that kind of funky fraction is equal to y, and now we found its inverse. So here, when you have, an exponential inside of a logarithmic, it's not quite so predictable. What's that inverse going to look like? So we started with a base 2 inside of a log base 3 and finished with a base 3 inside of a log base 2. This type right here doesn't really have much of a place in terms of a small part of a bigger problem. That's just like a difficult inverse problem for the sake of practicing all your rules in one question. These guys here, a little bit more common to have these guys be the smaller part of a bigger problem. All right, that wraps that up for today.